Hi, my name is Matthew, and in this video I want to talk to you about rational expressions and rational functions. A rational function is one where the numerator and denominator are each composed of their own polynomial function. And the first example that we see here gives us a polynomial function f of x equals x plus 3 over x minus 4. And what we're asked to do initially is to evaluate this function for an x value of -1. And we're told that because we see f of -1. So if we plug in a -1 in the numerator for our x value and add 3 to it, and -1 goes into the denominator, and we subtract 4 in the numerator, we end up with 2. In the denominator, we end up with -5. And that's our solution, no problem. Now in the next evaluation that we're supposed to do, plugging in an x value of 4, the 4 going in and being added to the 3 is no problem, but in the denominator, a 4 minus 4 poses a problem. 7 divided by 0 is not good because this is undefined. So the correct answer for this evaluation, f of 4, would be undefined. And as we move into talking about the domain of rational functions in problem number 4, making sure that we avoid plugging in x values into our function that cause it to be undefined is pretty much our primary objective. So when you have a rational function, and you know it's a rational function because there's a variable in the denominator, you always want to be on the lookout to make sure that you exclude x values, in this case, that would cause your denominator to equal 0. And what would those x values be? Well, we can find that out by taking the denominator and setting it equal to 0, and then solving this little equation. We add 4 to both sides, and we get x squared equals 4, and then we take the square root of both sides to find that x equals the square root of 4, which is, if you said 2, you're half right. The other half is -2. So we want to avoid x values of positive or -2, because -2 squared, in other words, -2 times -2, also makes positive 4. So we're going to leave that one out of the domain also. Now, this is set up a little bit incorrectly because Part A is asking us for our solution in interval notation, and then we see a number line. So let's work with the number line first. I want to leave out x values of -2 and +2. So I would put an open circle at those, and then I would shade all the rest of my number line, all the way to the left of -2, shading in between negative and +2, and all the way to the right of +2. So that would be my answer on a number line. Now, when we take the number line and we translate it into interval notation, in order to leave out those two values, we're going to use parentheses. So even though option B here says set builder notation, let me just cross that out for the moment. And let's say that interval notation is what we're writing here. Well, actually, why don't I do interval notation here? And the list of acceptable x values to plug into our function consists of all of the x values starting at -infinity, coming up to -2, excluding the -2 with a parenthesis, or, that's the union symbol, or we can choose x values starting at -2, but excluding -2 with that parenthesis again, coming all the way up to +2, excluding +2, or again, we could choose x values starting at +2 and going all the way up to +infinity. So this would be the answer to what is the domain of our function using interval notation. And finally, set builder notation. You'll see some variety in the presentation of a solution using set builder notation. If I were to write the domain of this function using set builder notation, I might write the set of x values such that x does not equal -2, comma, x does not equal +2. So it's very different. Well, it's the same. It's equivalent to what we just wrote using interval notation. But in interval notation, we essentially gave a list of all of the x values that we are allowed to use. And what you're seeing in set builder notation, the way that I wrote it, is I'm really giving a list of x values that I'm not allowed to use. But in the end, it's the same list. And what we're really getting at is a list of x values that we are allowed to use. So this is really the set of all the x values except negative and positive 2. That's a lot of x values. All right, let's take a look at number 5. Again, we're seeing the variable in the denominator, but we want to make sure we don't divide by 0. But look at this. If I take a number and I square it, pick any x value and square it, you're going to get a positive number, because a negative times a negative makes a positive, and a positive times a positive makes a positive. So x squared will be a positive number. Unless x happens to be 0, then 0 times 0 is 0. 0 is not really a positive or a negative number. But at the very least, there's no way that x squared is going to be negative. So we've got a non-negative number plus 3. That 3 is definitely going to push us into the positives. In other words, x squared plus 3 will always be greater than 0. So there's no danger of division by 0. Therefore, our domain, the list of x values that we're allowed to plug into this function, the domain consists of all real numbers, from negative infinity to positive infinity. So whether that means you're shading the entire number line, or in interval notation, you would list from negative infinity to positive infinity. Or in set builder notation, I don't think I would ever give my answer to this question regarding the domain. In set builder notation, sometimes you might actually see it printed all real numbers. That's a possibility. You could also see the capital R in here, which is a blackboard R with sort of a double bar on the left-hand side. You could see negative infinity is less than x is less than positive infinity. But whatever you see as far as an answer in set builder notation, if it were a multiple choice option, make sure you're choosing the one that indicates that you can use any x value you want to. From there are only some slight variations. In problem number 5, we still need to make sure that x does not equal 0. How do I make sure that that happens? The first thing I would do is look for the x values that would make my denominator equal to 0, and then make sure to exclude them. So factoring the denominator, setting it equal to 0, getting an x value of positive 4, an x value of negative 3, and those are the ones we want to leave out. So in interval notation, well, on the number line, we need to leave out negative 3 and leave out positive 4, so those get open circles, and we would shade everywhere else, all the way down to negative infinity, everywhere between the two, everywhere to the right of positive 4. In interval notation, from negative infinity up to negative 3, or the x values between negative 3 and positive 4, or any of the x values from 4 up to positive infinity. So that solution, that domain looks very similar to the first one that we saw. In problem number 6, same thing. Take the denominator, set it equal to 0, factor. This is really turning into more of a factoring lesson. X squared minus 36 is a difference of squares, so it factors into a plus b times a minus b, which in this case is x plus 6 times x minus 6 equals 0, which gives you x values of negative 6 and an x value of positive 6. Those are the x values that you want to leave out of your domain. They get open circles on the number line. and then translate that into interval notation. Now in problem number 6, before I go on to the next one, I should point out that once you factor the denominator, you could rewrite the original function h of x as x minus 6 over x plus 6 times x minus 6. And you'd think, well, I could cancel out these x minus 6's and I could put a 1 then into the numerator, and my function h of x really becomes 1 over x plus 6. Therefore, the only x value that I really need to avoid is an x value of negative 6. It's not true. When we evaluate the domain of a rational function, you need to evaluate the domain before you simplify the fraction. Now, if it were a conversation about asymptotes and wholes on the graph, then it would be worth noting that the x minus 6 and the x minus 6 cancel out. That would show up as a whole on our graph where x equals positive 6, whereas this factor sticking around in the denominator would result in a vertical asymptote at x equals negative 6. So again, for asymptotes and wholes, we need to watch for the ability to reduce our rational function. But when it comes to looking for the domain, we need to consider the denominator as it is initially, maybe factoring it as a first step, but don't reduce before answering the question about the domain. Problem number 10, factor the denominator, set it equal to 0. Looks like plus 7 and minus 5. And that's it as far as example problems where we're talking about the domain. Number 9 is Number 9 is a simplification question. This is just kind of a throwback to give us the opportunity to remember how to deal with exponents when it comes to reducing. So this is not directly pertaining to this section that I'm covering in my class, but it's a good idea to remember how to reduce rational expressions like this. The 6 over 12 reduces, leaving us with a 1 in the numerator and a 2 in the denominator. 6 over 12 equals 1/2. The x squared in the numerator divided by x to the first power, we know that we need to subtract our exponents. So this 2 minus the invisible 1 on the x gives us x to the first power. Reducing here, you're going to cancel out 5 factors of y on the top and 5 factors of y on the bottom, leaving you with 4 factors of y in the denominator. So you could write y to the 4th in the denominator, or you could do the upper exponent minus the lower exponent. 5 minus 9 is negative 4, and write it as y to the negative 4 in the numerator initially. Same thing with your factors of z. We can write this as z to the negative 4. 3 minus 7 makes negative 4. As a final answer, it's pretty typical to write the expression using positive exponents, and so I would write this as x over 2 y to the 4 z to the 4. Alright, that is a fully simplified version of that rational expression. And then one more little bit of simplifying that I want to look at with you, and that will wrap this video, is simplification that involves a factor of negative 1. So in the numerator, in number 14, you notice the pretty typical expression where your exponents are in descending order. We're starting with an x squared, and then we have an x to the first power, and then x to the 0 power, in other words, our constant term. But in the denominator, they're in reverse order. So one thing that you can do so that this looks a little bit more palatable would be to leave the numerator as it is. Well, let's factor it as long as we're at it. No, don't do that, because I want you to see what it is that I'm really focusing on. So I'm going to leave the numerator as it is for the moment, and I'm going to factor a negative 1 out of the denominator, which makes the positive 14 into a negative 14. The positive 5 or negative 5x becomes a positive 5x, and the negative x squared becomes a positive x squared. So by factoring out a -1, I changed the sign on all of my terms. Now it makes even more sense to rewrite those in descending order. X squared plus 5x minus 14. At this point, I would simplify. Do we have some more room over here? We do. All right, so let's say equals, and let's do some factoring. In the numerator, we have x plus 3 times x minus 2. In the denominator, there's the factor of -1, and then 7 and 2 look like they will work. X plus 7 and an x minus 2. Now, we're not being asked about the domain in this problem, so we don't even need to hardly think about it. We can simply cross out the x minus 2's because x minus 2 divided by x minus 2 equals 1. So what we're really removing there is a multiple of 1, leaving us with a final answer of, and here's where you have some options. You could write this as, well, don't write your answer with a highlighter like I just tried to do. You could write your answer as negative and then put your fraction bar with the x plus 7 on the bottom and the x plus 3 on the top. And this would be a very acceptable final answer. How else might the final answer appear? I suppose it could appear as x plus 3 over negative x plus 7, or you could distribute the negative sign in the denominator and write it as x plus 3 over negative x minus 7, but my guess is that you're going to see it written either this way or maybe this way. But I'd say probably the first one that I drew a box around. The strategy in number 15 is identical. In the numerator this time, I'm going to factor out a -1 so that we can change the order up there. So I'll write negative x minus 2. Now I didn't talk my way through that switch in the numerator that I made, so let's have a look at it now. And let's distribute. What is negative times positive x? I would say negative times positive x would equal negative x. And there it is. And then let's distribute again. What's negative times -2? Negative times negative makes a positive, so that should be positive 2. And there it is. So you can see that in one step, instead of in 2 steps, I factored out the negative and I changed the order of my terms. Here I did that in 2 steps. I factored out the negative and then I changed the order of my terms. But in this problem, I did it all in one go. Now that I've done that, I'm going to do what we did in the previous problem. Now we're at this stage. I'm going to factor. So let's come back over here and factor. This gives us the chance to be reminded of how to factor a difference of cubes, which you need to commit to memory for success in an algebra class. I'm going to leave my negative times my x minus 2 in the numerator, and in the denominator, I know that factoring x to the third minus 8 gives me x minus 2 times x squared plus 2x plus 2 squared, which is 4. The x minus 2's cancel out. If you'd like to do that, you may. Or you don't have to cross them out. You can just come down to the next line and write -1 over x squared plus 2x plus 4. And that is a great final answer. Or this negative sign could appear out here as negative, as sort of negating the whole fraction, which would leave you a +1 in the numerator. Either way, I would not hesitate in a free response situation to present that as a final answer. That, ladies and gentlemen, is a wrap, as they say. I hope that serves as a good introduction to you when working with rational expressions and rational functions. Don't forget that when you're determining the domain of a rational function, to answer the domain question before you simplify the fraction. And when it comes to factoring, you can always double check to make sure that you factored correctly by multiplying it back out and seeing if you get your original expression. Thanks so much. See you next time.